With regard to the origin of life, are you able to link the idea of nanostrings with the first replicators?
Yeah, well, the first replicators were nanostrings, right? They were either RNA, they had to be nanostrings. They were either RNA or DNA or something similar to that. This is, this is one of the things people are starting to investigate now. So you don't only couple a structure that can survive at some moment, probably RNA, because it's able to catalyze chemical reactions, starts to make copies of itself. So people are working actually on the physics of all this. We now know that it's thermodynamically favorable to become a replicator. So the universe will push matter to become replicator because you dissipate more energy, and it looks like in this way you can use the energy better. So the universe created life. So embedded in the complexity of the nanostrings at the moment life emerged must have been the capacity to replicate. But of course, the very origin of life and the creation of a cell that supports that stable environment to create life we still don't know. You don't only need replicator molecules, you need a stable environment for the replicator molecules to survive. And we have no idea how that happened.
Thank you very much for the lecture so far. I was wondering, nanoparticles, are they sort of tiny, tiny particles, say, of a cell, a micro cell? Because I hear this, nanoparticles. What are nanoparticles?
Well, nanoparticle, most people understand my nanoparticle, this. Artificial structures made by chemists or material scientists that look like that. And they have nano size, so they have the size of a protein. But as I have shown you now, the key of life is not to be nano size, but it is this, the capacity to create movement at the nanoscale. That's why you cannot build one of these nano robots that go around cutting. You can make very primitive things that can move forward, and you can usually do it at the micro scale and use some of these principles, but you could never build anything artificial as clever as life. The only thing we can do, and we are starting to be able to do it, is this, what I just showed you before, this. So instead of creating something like out of metal or anything like that, you design something in your computer made of proteins, and you get biology to build it for you. And then you create an artificial structure, but actually is made of the same building principles of nature. So what we are learning is our cleverness to fabricate nature at the nanoscale fails. We can't. The only way we can build these nanomachines is by working with nature. I don't think we will never be able to create an artificial nanoparticle like that. And it wouldn't be useful. If you just have bacteria to make it for you, why would you create that top down? I think that's why we're having a very revolutionary change in the way we're creating technology. We can no longer, if we want to move forward, create technology in the way we did in the 21st century, top down. We need to work with nature. We need to understand nature complexity to clear the problems we have in medicine and with the rest of technologies.
It's just that they say that they use nanoparticles in cosmetics.
Yeah, it's just that drug delivery system. So basically what they do is to concentrate the chemicals in a small particle, so it's concentrated in one place. That's what they do. But it's very simple. It's basically a little ball, usually of the chemical, just put together into a nanoparticle. It's not sophisticated. It's just a way of concentrating the chemicals into one spot.
So you can push them, make them
more.
Very, very, very
Yeah, but
tight.
there's nothing very sophisticated.
Thank you.
Thank you. And I believe there was a question along that row as well.
It was kind of not 100% relevant. Why do tumours kill their host if they're reliant on it?
Because the cells are distracted. One of the things we are learning is that you start having a tumor when a cell in your body starts, for whatever reason, you've been drinking too much or you've been doing too much, and then start chemically changing, and it starts. Then it gets distracted, doesn't know what it is, and it starts reproducing very quickly, and then changes the behavior of all the cells around it, and they don't know anymore where they are. So we are a colony. We are a colony made of a lot of cells, and our cells of identity comes from walking as a person, having a brain. But the cells can feel as part of the whole and also as individuals. And as individuals, life only knows one thing: to keep moving. So you check your environment, you create computations for solutions of survival. And the solution of survival of a tumor is to start creating a mesh around it. So it allows it to survive. But one wonderful thing we're learning is that we can use things like not only chemicals, but electric fields or mechanical waves to revert tumors. If you go and look, we knew this in the early 20th century, but Michael Levin in the US is starting, or many people following him, showing that if you give a tumor, for example, electrical cues that mimic the electrical cues of healthy tissue, cells start to know where they are again, and they revert to the healthy state. Because the cells feel the environment mechanically, electrically, and chemically. And if you make them feel they're in the right place, they will behave like they are in the right place. The problem with tumor cells is that they're lost. And we have to find ways to get them to find themselves.
One of the biggest problems with modern medicine is the idea of antibiotic resistance. Can we use nanotechnology to overcome this?
I didn't have time for everything. Yeah. So as cancer cells, bacteria, even better, have been on Earth the longest than anybody else. So the billions of years. I think there's nothing more clever than a bacteria on Earth. We will never compete with the cleverness of a bacteria. Whatever you throw at a bacteria, it will evolve out of it, and it will continue living. So our antibiotics have this problem, that we took the antibiotics from fungi and plants and throw them, and bacteria grow resistant to them. So what people are doing with nanotech and with physics is to try to use several tactics at the same time. So instead of just using chemistry, they're using, for example, at the shape of the bacteria. And then they create nanoparticles that find those weak points in bacteria and combine chemistry with physics to kill them. And people are finding that when you combine several tactics, it's easier to avoid antibiotic resistance. But again, I think we're going to have to think much more cleverly about bacteria. We really need to embrace bacterial complexity. So our antibiotics maybe can evolve at the same time as the bacteria can. But yes, nanotech is being used, and there are nanoparticles that are used together with drugs that are becoming quite effective. And I just show you an example during the talk of nanoparticles that are put in immune system cells. So when you have sepsis kills you in most of cases when you have total blood poisoning. So the problem is that MRSA or other bacteria, when the immune system engulfs them, they're able to get rid of the action because they have evolved against them. So these people use nanoparticles inside the cells to go against that evolution of the bacteria. So of course, people are thinking all sorts of sophisticated ways of combining nanotech with traditional medicine to kill bacteria.
Thank you. And we have a question on the right-hand side here.
Some months ago, we had someone here who was talking about understanding the chemistry of photosynthesis.
Yeah.
And they were saying we aren't too far off knowing most of the stages of photosynthesis and involving electron tunneling and so on.
Yeah.
But the ultimate aim seemed to be to improve photosynthesis and maybe even to generate electricity directly from a version of plant cells. I don't know whether anyone's researching that or not.
Yeah, well, of course. I mean, basically, I didn't put this here, but quantum computing is also getting information from photosynthesis. So, yeah, we are learning a lot about, and it's done always by proteins with our nanomachines. And people are, I think, eventually will harness, in the same way I was saying, people are using the immune system and everything else. Probably we will have some hybrid system that combines the proteins that you can find in bacteria or in plants that are able to make photosynthesis with nanostructures and bigger materials. People are certainly working on that. It's unlikely, maybe it's too difficult to create artificial photosynthesis. Maybe it's in the same way as with the virus. Maybe we just have to work with nature and find where we can improve nature, and use nature is probably going to be cheaper. But certainly people are trying very hard. And also, they're trying to learn how photosynthesis is able to produce quantum computation at high temperatures. Because one of the problems of quantum computers is that they go at very low temperatures. So many people think that actually the future of quantum computers will be inspired by plants.
Could you explain again how this person managed to guess the shape of the protein?
Again, who gets the shape of the protein?
When everybody else couldn't in this...
David Baker. Okay. So, this is many years of research. So, so in protein folding, you start with a string, right? And you know the sequence of the string, you know the building blocks of the string, and then you try to make a computer program that is able to calculate the shape of the string, which can have the shapes I showed you before here, right? The incredible myosin or anything like that. So for most of the time, people just were trying to see, just by getting the building blocks in a simulation coming together, if they could fold it. And the problem is so huge. Basically, exploring all the possible conformations of the protein will be many times the age of the universe. So this is not something that happens in nature, and definitely is not something we can compute. So what these guys found was that during protein evolution, they didn't look at the proteins, they look at the genes that produce the proteins. And they look at the bits of the genes that were evolving together during the history of evolution of that protein on different animals and different living organisms. And from there, they sort of found couples of bits of protein that have always evolved together. And they sort of figure out those could work as kind of as staples during evolution, staples. So they put that into the computer program, so they managed to reduce the computer power they needed to fold the structure. And now they fold every structure. I think they're still not totally predictive, but in a few years they will be pretty much able to predict any protein structure. And that not only opens the way of a new way of medicine and understanding ourselves and predicting all the proteins that exist, but as I talk, opens an radical new way of producing matter. Because now we can do it in reverse. So we can produce any structure you want, that it will assemble in any structure you want from the computer using protein.
I've got a question just on more on the origins of life. You sort of walked us through the building blocks and the environment that you needed to create life here on Earth. And quite topical in the news is the plan to go to Jupiter and the moon there. And I was curious to know what probability you assign that they'll find life there.
Yes, so people are trying to go to Europa, actually, to look for life. I was actually involved in some of these conversations about how to find life in Europa. Actually, what I was proposing was a mechanical experiment with an atomic force microscope. One of the characteristics of life, and also of our intelligence, is like biological matter is constructed up from nanostructures all the way up into bacteria, into cells, or into living things in a hierarchical way. We're created up, down, and embedded in this hierarchical structure is the capacity to feel the environment. The environment creates us, and to evolve with the environment. So I think one of the characteristics of life, regardless of its chemical composition, is hierarchical arrangement. And you could measure that with a mechanical measurement, actually. So I was proposing some people that maybe we could just tap very fast into whatever matter we find. And if we find something, actually, one of my students here, I don't know where she is, Alba, is working in these techniques. We think we can get a signature of matter that is hierarchically structured, has a special mechanical design that some unstructured matter would not have. I'm not sure we're going to succeed. One of the problems of sending very sensitive devices to look for life is that they don't survive the crash. And this is one of the reasons atomic force microscopes, like the ones I showed before, are in Mars right now. So the Mars rovers have atomic force microscopes because they're very robust equipment, and they don't have infrared spectrometers or other spectrometers. I think they do, but it's difficult to carry out an optic device and survive, but it's easier to bring a mechanical device. There's a lot of thinking about that.
So,
You can have that, yeah.
So in your work, do you use quantum mechanics?
No.
And so, or is quantum biology a subject on its own?
I think quantum biology is probably important. And nature, we used everything to create life. In all these nanostrings that gave the origin of life, chemistry, mechanics, electricity. And quantum will be part of it. As I said, all throughout, a key characteristic of life is, movement through time. We're just starting to understand how the origin of time actually emerges from quantum interactions of matter. I don't think quantum can be ruled out, not only in practical ways, but in fundamental ways about the way the structure and the time in the universe emerges. And as such, maybe in many years, life might be a kind of probe of the meaning of time. If you realize the reason time for us goes forward is because we emerge from a non-equilibrium thermodynamic system. What does it mean? So I told you about the strings. So in order for the strings to store information, they need to move. They need to dissipate energy, right? If the strings were perfectly elastic, they didn't dissipate energy, everything was instantaneous. If there was no time, there would be no life. The reason our time goes forward is because we need to throw some of our energy into the environment, and that energy is used to move. As soon as you move, you create time. Our time goes forward because we emerge from movement. We emerge from throwing energy into the universe. Quantum mechanics is at the very base of the origin of life. We just don't understand how, because we still don't understand how matter interacts with each other to create time or to create energy. But this is physicist thinking of life. But indeed, people are thinking of applications, I just said, in quantum computers and another beautiful quantum mechanical effect is like the birds know the north. And the reason they seem to know where the north is because they see it. They seem to have a pigment in the eyes, which uses a quantum mechanical effect, that the magnetic field of the Earth changes, the mechanical changes the chemistry of the eyes, and they can see the north through quantum mechanics. So quantum mechanics is everywhere, of course.
The golden ratio is well known in nature, the golden spiral. The question is, do you use the knowledge of the golden ratio in your
work?
nano technology?
I work in plants, remember?
I'm so sorry?
I work in plants.
You do use it?
I work in
but
plants.
Is it used, though, for your research?
I don't do gold. I'm a physicist, and for me, maths always comes after the universe. I love maths, but when maths conforms to physical reality, in that sense, the golden ratio is interesting as a consequence of the structure of matter, right? So yes, I'm very interested in how biological systems, such as plants here, create their shapes and create their proportions as they use energy. So one of the things I study is how a plant, I measure with my AFM, is using non-equilibrium thermodynamics, is using energy dissipated, energy stored, elasticity to use the energy to create shapes, and how that shape interacts with the environment. Yes, there comes maths. There's some wonderful maths there we don't understand. We don't understand as a physicist. As a mathematician, you always understand things because you just multiply and square. But but the important thing is why nature creates this, right? I'm a physicist.
I just wonder whether you also combine pi with the golden ratio.
Yes, I haven't. But look, I didn't have time, I didn't finish, but I tell you something, you talk about golden ratio. I had this prepared. I have a friend, a sculptor, who makes these sculptures. And once he was asking me to do something for him, and the first thing I realized is that my plants fit in his sculptures. And you know what? His sculptures use the golden ratio. So now I can answer your question. Golden ratios are in people's heads, like yours and my friend's sculpture, but they're also in nature. And maybe that's another going back to the fabric of the universe, why the universe creates lives and why mathematics works, which is the biggest question, right?
And so this can be used in creating your mathematical models.
Agree. Yeah. We're still far from that, right? In a way, I think what we are learning about intelligence and how intelligence is created from biology and how from there we reach mathematics and our brain is able to produce mathematics is one of the most beautiful questions we have forward in the 21st century. We're getting closer to maths, which is quite wonderful.
I discovered that all the planets, the distance between all the planets is a function of both pi and phi in collaboration.
One of the things I say in my book is that actually by bringing biology back to physics and back to maths, we are reconnecting with the early civilizations. Because we are reconnecting in, for example, in Semitic cultures. You have this idea that God is sitting inside of you, your language reproduces the thinking of God. That's why you can translate the Quran. And this is something we're learning with machine learning. The structured universe is in our head. That's why our algorithms can translate our languages. So I think the moment we entangle biology with the history of biology on Earth, with evolution, with the structure and the structure of the universe, we come to the most primitive questions. Why pi and what phi, right? The origin of maths. So a lot of work for the 21st century.
So drawing a parallel maybe between physics and biology. So up to about 100 years ago, physics was going through a sort of reductionist phase and things were getting simpler and partly working out what...
Then we stopped with superconductivity and condensed matter physics.
Then it started to get more complicated as you got back
after
down
the
to a very
Second
small
World
scale.
War. Yeah, after the
and then it started to get very complicated and people had to develop a whole new way of thinking with quantum mechanics, which seemed very strange and unexpected and probably now not fully understood. If you now look at biology, maybe running 100 years behind, what do you think are the tools and the new ways of thinking that would be equivalent to quantum mechanics, the maths around that, or maybe the symmetry?
The convergence of sciences and technologies into biology is changing a lot of things. So, like the mathematics that we needed to understand reality from physics were pen on paper and simulation. I think the eruption of this understanding of intelligence that we're starting to have now, we still don't understand why deep neural networks are so good at doing it. I think one of the most beautiful things happening these days, for example, there's some theoretical physicists in Oxford, my department, that now they're starting to look at why they've been looking at other problems, why machine learning works so well. So basically, physics is also converging with biology in the origin of intelligence. Why can we learn? What can we learn? What can we get algorithms to learn what type of things? So we're going to see a convergence of the mathematical sciences as well, I think. As we're going to have to live in both worlds, the reductionist world of the parts and the complexity world, because that's how we come into being. Our brain, and looks like nature, requires simplicity and complexity at the same time. So I don't know. I think we will have a very different way of doing mathematical modeling in 20 years from now. And also mathematical thinking and about nature. And then nature, we're learning so much about quantum mechanics. We have so much information that we didn't have before about the structure of the universe. We're starting to build the first machines that start to be able to help us in the calculations. So most of my students right now are totally interested in learning machine learning algorithms. We all now, it's starting to be standard. Everybody now is able to, you can download your Python code, everybody going to do this. This will transform the way we think about higher maths as well. We have more tools. Will be more convergences. I just don't know. It will be very complex what we're going forward. And biology will be, biological departments, computer science department are full of people working on biological complexity. I collaborate with engineers, with computer scientists, with applied mathematicians, all trying to solve plant shape, tumor shape, drug delivery, how we model this, how do we build machine learning. It will be a very big complication of mathematical modeling, artificial intelligence, computer modeling. At the same time, we're going to be able to get much more information around, so we will feed into the algorithms loads of information with our biosensors. Those algorithms probably will evolve. We're going to start to be able to harness into the computer simulation evolution, as I just showed. And it might happen quite fast, 30 years, 40 years. So we're moving into a new realm.
It's a lot of machine learning.
Initially, I think it's still very crude. It's still just nodes and trying to mimic a structure. Imagine when I show you the molds and I show you these wires. Imagine maybe we don't need to build the algorithms anymore. We're just going to be able to grow molds with wires, combinations of all of it.
So just
certainly IBM is working on this. I think that really the boundaries between disciplines are shattering. Not in the biology departments, where they keep very into themselves, but material scientists are learning biology, engineers are learning biology, because it's how the universe creates matter, intelligence matter. And now finally we can start to crack it. That's all we all do. We're starting to just try, even the people that don't learn biology are using the consequences in their algorithms. So we're moving to a new way of doing physics.